Okay, well, happy Monday. It is it's week 8. Time doesn't stop for anybody. All right, well, I don't know. Does time even exist inside a black hole? It just stops? I don't know. What's the I don't know. I guess if there's no I don't even know. Okay, well, anyway. I made that offhand remark. Time doesn't stop for anybody. And I go, maybe that's not actually true. But anyway, all right. Anyway, it's week 8 Monday. Time is not stopping for us. So here we go. We're going to continue on talking about numeric optimization. I introduced a little bit of this concept of numeric optimization on Friday. We said, hey, you got a function and you want to find the local min or local max of the function. What do you do? And we just said, hey, well, you know what we did in calculus is we took the derivative and we set the derivative equal to 0 and we solved, right? And we're basically doing the same thing. We said, hey, take the derivative, and if you don't know how to take the derivative, that's okay. We can approximate the derivative with this function. And then now that you have that derivative, find the roots, and we have these root finding methods. And that'll work, okay? But again, you know, sometimes root finding methods don't work great. Sometimes getting your derivative is tough. So we have a little bit more of a robust method. It's called golden section search. And this is kind of, it's a bracketing method. So the most robust method that we had for root finding was bisection method. And we said, hey, if it goes from a negative side to a positive, we know there has to, and it crosses, we know it has to cross, you know, y equals 0 somewhere in there, and we can find a root. And we just kind of shrink that thing. We split our interval in half at every iteration, and that worked, okay? And that one was guaranteed to find the root. All right, golden section search. Guaranteed to find a minimum, okay? And it starts by, you have an interval and it shrinks, okay? And golden section search uses the golden ratio. So let me talk a little bit about the golden ratio. So here's a rectangle, and this rectangle is the golden ratio. And the idea here is, here's a rectangle, and what I'm going to do is I'm going to cut off a square. All right, so here's the golden ratio. I cut off the square, and then what remains, this portion that remains after I cut off the square, has the same proportions as the original rectangle. Okay, that is to say, the short length, so okay, the big square, the short length has a length of 1, and the long length has a length of 1 plus x. Okay. After I cut off the square, and we look at this smaller rectangle over here, the short length has a length of x, and the long side has a length of 1. So the idea here is that this rectangle has the same dimensions as the big rectangle, and so we're going to say, you know what, if I take the short side, which is for the big rectangle is length of 1, and I say, okay, length of 1 to 1 plus x, the long side, basically the blue length to the long length is going to have the same ratio as the blue length to the long length, the blue to the red. So this length x over here to 1. So I can say 1 over 1 plus x is equal to x over 1. So we have the same kind of proportions, same dimensions. And we say, okay, well, if you do that, how long should x be? How long should x be? So this is just a little bit of algebra. I do 1 over 1 plus x is equal to x over 1, or equal to x. Solving for x, I multiply both sides by 1 plus x, subtract 1 from both sides. Now I have this quadratic polynomial, and we're going to solve for x using the quadratic equation. Or is it quadratic formula? I don't know. What? It's a quadratic formula. Okay, all right. So we do this, and we get well, you get plus or minus, but we'll take the plus one because x is a positive distance. So we get -1 plus root 5 over 2, which is 0.618. Okay, 0.618. And we see, oh yeah, that actually is true. If you plug in 0.618 here, okay, or approximately 0.618, 1 divided by 1.618 is 0.618 itself. Okay. Another neat little consequence of this is that if you do 1 minus 0.618, you get 0.382, and that's equivalent to 0.618 squared. Okay, so if you do, I mean, there's more. It's irrational, so there's more decimal places. But if you do 0.618 squared, you get the same thing as 1 minus 0.618. So 1 minus x is the same thing as x squared, and this is a handy and very useful feature that we will use moving forward with golden section search. So so this is how it's going to be. All right, we're going to just start off with a very, very simple function, x squared minus 0.8x. And I mean, visually, I've plotted this, and we could see, okay, the minimum is going to be right here at 0.4, right? But we're going to search. We're going to search for the minimum using golden section search. We're going to say, all right, here's an interval. Let's find the minimum value. Okay, and so we start off with an arbitrary interval, and I guess the premise here is that within this interval there is one local minimum. Okay, we're going to say between 0 and 1 there is one local minimum. Okay, and we don't know where, but we're going to just say there is one local minimum between 0 and 1. Okay, and so 0 is going to be my left-hand side, 1 is going to be my right-hand side, or this will be my upper endpoint and my lower endpoint. Okay, and the way golden section search is going to work is we're going to select two interior points, and we will evaluate the function at these two interior points. And the way we're going to pick the two interior points is we're going to use the golden ratio. We're going to go basically 0.618. So if my golden ratio is 0.618, I'm going to go 0.618 of the way from 0 to 1. Okay, so I'm going to end up around here. And then I'm going to go 0.618 of the way from 1 down to 0. Okay, so if you have the left hand side and the lower bound and the upper bound, and phi is your golden ratio of 0.618, you're going to go about 0.618. You're going to go 0.618 of the way from the lower to the upper side. So I'm going to do lower plus 0.618 times whatever u minus L is, and then we also go 0.618 of the way from u down to L. So I go u minus phi times 0.6 u minus L. Okay, so in this case, in this picture, it's 0 and 1, and so my x1 is going to be at 0.618, and then x2 is going to be 1 minus 0.618. I'm going to end up at 0.382, right over here. All right, is that okay as far as where my interior points are going to be? So those are my two interior locations, and I evaluate the function at those two interior locations. So x1 is right here at 0.618, x2 is over here at 0.382, and I evaluate the function at x1 and I evaluate the function at x2. And what I find is that the function at x1 is higher than the function of x2. So with that piece of information, I can now shrink my interval. What I can do is I can say, if between 0 and 1 we're going to have one minimum value, I can throw away everything to the right of x1. Why can I do that? All right, I can say the minimum that we're looking for has to be between my lower bound 0 and x1, which is 0.618, because I know there is a point between 0 and x1 that's lower than f of x1, okay, and that's x2, right? So I could throw away everything to the right of x1, because if we said, hey, there's a minimum value between 0 and 1, and if I evaluate x2, I know x2 exists. x2 is a point that's lower the function is lower at x2 than it is at x1, and so there is a point that's lower than f of x1, and so the minimum, wherever it is, has to be between 0 and x1. Okay, and I can throw away everything to the right. Okay, the minimum value can't be to the right of x1 because we know this point exists, right, and it produces a smaller value. So I'm going to throw everything away to the right. Okay, and so now my new interval is going to go from 0 to 0.618. Right? So I'm going to make x1 my new upper bound. So 0 remains my lower bound, and now x1 becomes my new upper bound. Right? And then so now that I have a smaller interval, I'm going to just repeat the process. I need to pick 2 interior points and that I'm going to evaluate. Right? And this is where the genius. Oh yeah, question.
Yeah, would this work for any function? Because couldn't a function just like go sharply down and then back up after x1?
It could, okay, and it still works. But so I think it's easiest to explain by saying we're going to just go under the assumption that there is just one minimum value, okay, one minimum value in some interval, and if you go off with that thing and you say within this interval there's just one minimum value, then we can keep kind of throwing away things. If you got this thing where you're talking about and you have multiple minimum values in a thing, then the logic won't apply. So this will find a local minimum no matter what. It might end up in the initial stages, it might throw away a particular interval where there was even like a global minimum in that thing. But if you just say, hey, within an interval there is a local minimum, this will find it. Okay. So anyway, I'm going from 0 to x1. I got to find 2 interior locations, right? And this is where kind of the genius of using the golden ratio comes in. So basically, I want to go 0.618 of the way up to the upper bound, and I want to go 0.618 of the way from here down to the lower bound. And do you remember 0.618 squared is 0.382? Okay, so now that my upper bound is 0.618, if I want to go 0.618 of the way from the lower bound to this new upper bound, that ends up right here at x2. Okay, so that's what I'm trying to show here. So when I say if this is my new lower to upper bound here, 0.618 of the way from down here up to here ends up being exactly at x2. So I don't when I calculate my 2 interior locations, I can just reuse some of these existing content. Okay, I don't have to calculate 2 new locations and go through the work of calculating the function at those 2 new locations. I could just say, oh, these values that I used to have, I can just reuse them again. Okay, and I repurpose them, which is good from an efficiency standpoint, right? So if you had some kind of job and you had to do this repetitive task, but at every kind of task that you had to repeat, you were able to reuse some of the previous stuff. That's a lot better than having to like create 2 new things every single time. Okay, and so so you can see this is going to hold up, right? So your new x1 is equal to your old x2, and that my lower bound was 0 plus 5 times this, and I end up getting 0.618 squared, which is 0.382. Okay, and so I can reuse the old x2 and f of x2 values. I don't have to recalculate that, so I'm going to reuse that. I still have to kind of calculate a new value over here. So going from lower and upper bound, I'm going to have to go 0.618 of the way down to here, and that takes me to 0.236. Okay, and that's fine. And I evaluate the function at this new location. Okay, I'm reusing the same value here, and I say, oh, you know what? This value is higher than this value, so therefore I can eliminate everything to the left of my new x2 value. Okay? And so my interval shrinks down to there. I can throw everything away there, and I can say, okay, the minimum has to be between now 0.236, and 0.618. So I can say the minimum has to be somewhere in there. Okay. And we'll eliminate everything to the left of x2, and then I just kind of repeat the process. So now I'm going to reuse this value right here, okay, and I will calculate a new value over here, and we kind of keep going, okay. And so you'll notice, so between here and here, the blue dot is higher, so I'm going to throw away everything to the right, and what you'll notice is that this dotted line right here at x2 is going to get reused, okay. It gets reused, so this line at point whatever 318 gets reused, and so now I calculate a new thing. If we look at this, we could see this value is higher than this value, so I'm going to throw away everything to the left of this line over here, and this line right here will get reused. And now I have two things, and we're going to calculate here and here. I think it's hard to see, but I think this value right here is a little bit higher than the value over here. So we're going to throw away everything to the left of over this. And this dotted line right here is going to get reused. Okay, and we just kind of keep going. We'll throw away everything to the right. The dotted line gets reused, and everything kind of shrinks. Okay, so every iteration, we throw away some section to the left of the dotted line, and then the other dotted line gets reused as one of the next dotted lines. So you'll look at that. Okay, and it just keeps shrinking and shrinking, and our interval gets smaller and smaller and smaller until we say, okay, I'm satisfied. We can stop here, and we will say our local minimum is within this interval here. Okay, so golden section search is very robust. If a minimum lies within the interval, golden section search will find that minimum value. Even if the minimum value is on the boundary, then the interval will keep shrinking and converge to that boundary point. Okay, one of the like the left lower bound or upper bounds. Okay, if you do have multiple minima within your interval, then yes, early on it might end up throwing away like one of the more, like if you have multiple minima, you know, and there might be like a global minimum, you might miss that global minimum, but it will eventually, it will shrink to a point where that assumption that there's one and exactly one minima in this boundary or in this interval, and it will converge to that. So it is guaranteed to converge to a local minimum. But if there's multiple local minima within an interval, there's no guarantee that it's going to converge to this particular one. Okay, but it will converge to a local minimum. So ideally, if you can say, hey, we know there's one local minimum in here, then it will work the best there. Okay, as far as how do you terminate, how do you stop the thing? Probably the most common choice is to say, hey, when the difference between the upper bound and the lower bound of your interval is, you know, less, you know, some very small amount, like 10 to the minus 5, 10 to the minus 6, then we'll call it a day and stop. Okay. I guess another thing is you can evaluate between. Yeah, that's probably the best criterion, but yeah, there might be, you can just stop after a certain number of iterations and things like that. But you probably just keep going until you reach some tolerance value there. Okay. Here, let me give you your first view quiz answer, which is the letter C. C as in cat. And let's here's some code that we have. So I found some golden section search code online, modified it a little bit, and here we have it here. Okay, and so this is a function that can take in other functions as an argument. So it will allow for you to put in some function f as an argument. You need a starting lower bound and a starting upper bound, and then it gives us a default tolerance of 10 to the minus 5 that you could change to something else. And then it says, all right, let's calculate the golden ratio phi here, which is -1 plus square root 5 divided by 2. And and it's going to take x1 and x2. x1 is going to be, so here's your lower. The arrangement points is x2, x1 upper. So we're going to go x1 is the lower bound plus phi times upper minus lower, and then x2 is going to be upper minus 0.618 of the difference between u and l. Okay, so now that we have x1 and x2, we will evaluate the function at x1 and x2. I'll call that f1 and f2. We'll start off at 0 iterations, and we will just run this loop. Okay, the loop runs until upper minus lower is less than some tolerance, then it will kick out. Otherwise, it'll keep going, and basically it just checks one condition. If the function at x2 is greater than f1, do all of this, and if it's not, meaning f2 is less than or equal to f1, then do all of this. So if f2 ends up being higher than f1, then basically our new interval is going to be x2 is our lower bound, upper remains the upper bound, and then x1 becomes kind of our new interior point of x2. So x2 becomes the lower bound, x1 becomes x2, and then I'm going to take the value f1 and I'm going to just reuse it to be f2. I don't have to reevaluate anything. I do need to calculate the new location of x1, which is going to be my now redefined lower bound plus phi times upper minus lower, and then I do need to evaluate the function at x1. Okay, and I'll do that. And now that I have all those values, I could go through and check this, run the loop again, check to see if this condition is true or not. Okay, if this condition is not true, then I do the opposite. We will end up throwing away everything to the right of x1. So x1 becomes the new upper bound, x2 becomes my new x1, f2 becomes the new f1. I need to calculate a new inner location, x2, and then I need to calculate the function at f2. So we do that, and my interval shrinks. I'll increase the number of iterations by 1, and we'll just let that keep going. At the end, I'll print out how many iterations, or I'll cat how many iterations ran, and then I will return the midpoint of my interval, lower plus upper divided by 2. Okay, so we could try this out. My very simple function, x squared minus 0.8x. Just from algebra or calculus, we know the true minimum is at 0.4, but we could just try it. We could say, hey, try it out between 0 and 1. And after 24 iterations, it says your minimum is at 0.3999999, which is pretty close to the true value of 0.4. Again, everything with a numeric method is going to bring us to an approximation. If I say, hey, you know what, I want my interval to be 10 to the minus 6 rather than 10 to the minus 5, then it takes 29 iterations to converge, and we get 0.400001. Okay. If I say I want 10 to the minus 7, it takes me 34 iterations. If I want 10 to the minus 8, it takes me 39 iterations. Okay. So if you want greater precision, basically you need more iterations to run. Okay. One thing you might have noticed is that like every additional decimal place of precision takes about another 5 iterations. Okay, going from 24 to 29 to 34 to 39. That's not a coincidence. That's the result of every time you run an iteration, your interval, the next iteration, the interval's around 0.618 of the previous iteration, right? So if you one iteration to the future, the width is 0.618. 2 iterations to the future, it's 0.618 of that, so 0.382 of the original thing. And so if you do 0.618 to the 5th power, that's around 9%. Okay, so if you want to go down to get 1/10 of what you started off with, so if you want to go from 10 to the minus 5 to 10 to the minus 6, so 1/10 of the previous thing, that takes about another 5 iterations to do that, right? So, kind of bisection method, you have this linear convergence. Same with golden section search. You've got linear convergence as far as how quickly does your interval shrink, or how quickly does the amount of error shrink with each iteration there. Okay, let's now talk about coordinate descent. I guess I'll go ahead and give you your second view quiz answer, which is the letter D. D as in dog. Okay, D. One method of optimization that we haven't talked about is grid search. Okay, this is kind of your brute force method. If someone says, I want you to find the minimum of a function, here's a computer, and if you had no understanding about math, you could do this via a brute force search, okay? Doing a grid search. And basically, what you would do is you would just evaluate the function at a whole bunch of locations, and you'd say, okay, I evaluated the function at a whole bunch of locations. This location produced the smallest value, therefore the minimum is right around there, okay? And that would work, okay? That's basically grid search. It's kind of, you just evaluate the function at a whole bunch of places and say, hey, which one of these things is the smallest? That's actually what's happening when you plot something on R, okay? So when I created this plot of a function, this is basically, I've done all the work of a grid search already. Because the way R plots a function is it evaluates the function at a whole bunch of locations, and then it joins those locations with little line segments, okay? So the computer actually doesn't have a fundamental understanding that there's a parabola, which is a nice smooth curve. What it's doing is it says, oh, here's the function here, here's the function at this point, here's the function at this point, here's the function at this point. I'm going to connect this with a line, connect this with a line, connect this with a line. And it's just, all those points are so close together that our eyes look at this and says, hey, that looks kind of like a smooth curve, right? But I mean, internally, these are all just pixels that are really just like little tiny little boxes. But they're close enough together, it looks like a smooth curve. But the computer is just evaluating the function at a whole bunch of points, okay? And so the work has already been done. And so here I just said, hey, what if I evaluated the function between -3 and +3? And I have a step size of 0.001 between all of these things. I could evaluate, the function at basically 6,000 locations, and I could say, hey, which value produced the smallest value? And it says index location 3,401, which corresponds to the location 0.4, right? But basically, all I've done is I've just evaluated the thing. And this method works and is fine if you don't quite understand, like, do I have a way to optimize a function, right? If I need to find the minimum of a function and I have no idea how to even begin optimizing the function, this could work, okay? And we might be in this situation when you have a multivariate function. So multivariate function, basically you have a function of more than one dimension, and I say, hey, give me the location that's going to give us the minimum value of a function. And you go, well, I don't know how to do that, right? And so you might be tempted to use a grid search. And the thing is a grid search becomes very inefficient in higher dimensions. Because if you're going to search from -3 to +3, you might have around 6,000 locations to search, okay? But what if you now have a plane, and you're going to go from the corner -3, -3 to the corner +3, +3, okay? Now you have 6,000 locations in the x direction to search, and you have 6,000 locations in the y direction to search. And so you have a total of 6,000 times 6,000, 36 million coordinates to search, okay? That's a lot more computation than just 6,000, right? Going from 6,000 to 36 million is a lot more computation. If you have a three-dimensional function, now you have 36 million times 6,000, you have 216 billion locations to evaluate, right? And so you can see this is going to become wildly inefficient very, very, very quickly, right? So yeah, the number of locations to evaluate grows exponentially with each dimension. And so when you are in a multivariate situation, we need something more efficient than just grid search, okay? And that's where we introduce coordinate descent, okay? The way coordinate descent works is you say, okay, you've got this multivariate function, this surface of whatever, and what we will do is we will reduce the multivariate function into a univariate thing. So basically, you just hold all of the variables constant except for one. Okay, so you have a function of x, y, and z. You would hold y and z constant, okay, and that reduces your function down to x, right? And so now you have a function of x. You will minimize this function of x. And now that you get a value for x, you will use that. And you will hold that constant. And then you'll say, okay, I'm going to hold x constant and z constant. And then we will have a function of y. You find the value that minimizes, value of y that minimizes the function. Now you hold x constant, y constant, and you let the function vary in z. You do that, and you just kind of repeat. You hold everything but one variable constant, so it reduces to a univariate function. I'll do a thing where I just have a function of two variables, x and y, and we'll start off by holding, one of these things constant. We'll have a function, we'll hold y constant, we have a function of x. Once I get x, I'll hold x constant, I have a function of y. Hold y constant, now I have a function of x, okay? So you just take this multivariate thing, hold all the other variables except for one constant. You get a univariate function, and then you optimize your univariate function, okay? So I will demonstrate this with some code here. I've got this code example, so let me pull up R. Okay, so here I'm going to load up golden section search. So here's that same kind of code that I have. I just got rid of the one line that prints out how many iterations, because I don't care how many iterations I have, but we'll use that, okay? So I'm going to go ahead and I'm going to source golden section search, okay? So there's my function. And so, I could do, if I say f is a function of x where, I want x squared minus 0.8x, okay? I could do golden on f, evaluate from 0 to 1, and it gives me, this is your location, 0.39999, okay? So that's basically what we'll have here. Let me remove that function f. Okay, I'm going to create some plots down in this this pane over here, and they're going to be generated using Plotly. Okay, and this is going to be the function that I want to optimize. It's a function of x and y. It's x squared minus 2x minus 0.5x times y plus 2.5y squared. Let's go to Wolfram Alpha. That work? Okay, so I guess this is the plot of the function. I don't know why the scaling is so weird. It's going from negative to 10 to 10 over here, and then 1 to negative 1 over there, which is a little bit weird, okay? Let's see. Global minimum is at this location 40 over 39, 4 over 39. And it gives us a few other properties here. I don't know why the contour plot looks all weird there. But anyway, this is what Wolfram Alpha has to say about that. But this is our function, x squared minus 2x minus 0.5xy plus 2.5y squared. Here I'm going to create a plot. You have to kind of create this matrix of these different locations. I use the outer function there. And then I'm going to ask Plotly to create a surface plot here. And we'll produce this. Okay. So this is what we have. So we have this paraboloid, which basically you can think of, imagine a parabola, okay, and then in the x direction, imagine a parabola, and then imagine another parabola in the y direction, and then fill out that kind of a bowl shape, okay. they might not necessarily, like they might not, the x and y might I guess the major and minor axes of the ellipse might not necessarily be parallel to the x and y axis. And so with Plotly, you can actually like rotate this thing. And so I don't know if you guys can see this. Let me try to orient this correctly. All right. So here, x, I'm going from negative, I guess, 1.5 to positive 3. And then y also, I guess, is going from down this, it's kind of hard to see, this corner over here is negative 1.5 going up to 2 there, okay? And so you can kind of see some of these ellipses here. It's a little bit hard to see. It's but in this direction we have basically a parabola over here, and then if I rotate it in this way, we also have a parabola in this direction, and you kind of have this you have this surface here. And so we want to find the global minimum. We want to find the minimum here, which is somewhere around here-ish. Okay, you can kind of see at the bottom of the bowl, and we will use coordinate descent. And so I'm going to just start at this arbitrary location of x equal to negative 1.5 and y equal to positive 1. Okay, so that's just an arbitrary starting location. So I'm going to do x0 is negative 1, y0 is positive 1.5. I'm going to add a dot there. Okay, and so that is right here. Okay, this orange dot is at x equal to negative 1, y equal to positive 1.5, right there at there. Is that okay as far as what's being drawn here? And what we're going to do is I'm going to hold y constant at 1.5. Okay, so I'm going to just say, you know what, this is a two-dimensional function, but what I'm going to do is I'm going to just hold y constant at 1.5, and that will reduce it to a one-dimensional function, okay, which is going to be a function of x. So basically, so I've intentionally written my code poorly, because and the reason for this is I want you to do this in your homework, and I didn't want my code to be so good that you can just copy and paste my code into your homework and be done with it. Okay, so this is a very silly kind of way to do it. I've defined a function called g for iteration 1, where I say y is equal to 1.5, and what we're going to return is going to be x squared minus 2x minus 0.5. 0.5x times y is going to be 0.5x times, and then I just replace the y with 1.5, okay, plus 2.5y squared, and so I replace the y with 1.5 there. Okay, so this is going to be my function. We'll go ahead and add that trace line here, and so holding y constant, you can see that univariate function now shown in orange here. Okay, so it's basically just this function right here. That's what it looks like. I guess I can rotate this around here. Okay, so this is just the line getting traced out on the surface here. Okay, and it's starting at this location. So now that I have a univariate function, what I want to do is I want to say, okay, what is the value of x that minimizes this orange line? Okay, what is the value of x that minimizes that orange line? And so here I'll just use golden section search. Okay, and when I do that, it says the value of x that minimizes it is 1.375. I guess let me go back to Wolfram Alpha, and I'm going to just plug in this thing. And so it does some computation. So I guess it simplifies to x squared minus 2.75x plus 5.625. This is when you put in all of these things, okay? This is what you get. And so, you know, the function is minimized when x is equal to, where is it? 11/8. Global minimum at 11/8 or 1.375. Okay, and that's what we have here. Okay, so I'm going to say, all right, let's plot that. Let's add that dot to the thing. Okay. No, sorry. So here, this white dot right here is where the orange function is a minimum here. Okay. Okay, so the orange function is minimized right there at x equal to 1.375. And now I'm going to hold x constant at 1.375. So I'm going to say g at iteration 1b, I guess. X is going to be 1.375. I'm going to replace all x's with 1.375. So this is just a function of y. And I'll plot that. So here's the function when you hold x constant at 1.375. This is what the function looks like. This parabola here, and we want to minimize this. Where is this function minimized? So basically I'm going to ask, hey, where do we do that? All right, so I plug that into golden section search. It says that function is minimized when y is 0.1375. So that's going to be somewhere around here, y at 0.1375, 0.1, 0.15. This is what we're going to have. So I'll go ahead and I'll add a little marker there. And that's going to be right here, okay? So when we say, hey, where is this white function minimized? It's right there, okay? It's a little bit hard to see, but I don't know. But it's also helpful that we can kind of rotate this and see where this thing is. Okay, so now that I have that, I've done one whole iteration, and I'm going to repeat the process. I'm going to say, all right, let's hold y constant at 0.1375, and when we do that, we get this yellow line here, okay? And we want to minimize this yellow line, okay? And we say, all right, where is this function going to be minimized? All right, and it is minimized at 1.034375. And where is that? That's going to be right here at this dot right here. And then and I've kind of stopped writing iterations, but we would just kind of continue this. I would draw another line that's parallel to the white line that runs through this point, 1.034375 right there. It would run through right there, and then once we do that, I would find the value of y that minimizes, and we would kind of keep taking steps, little incremental steps, as we get closer and closer to the I guess global or local minimum in this thing. So coordinate descent says, all right, you've got this multi-dimensional function. We will just hold all the variables constant except for one, and that reduces it down to a univariate function, and we can do univariate optimization. Here I've been using golden section search for univariate optimization. You could use whatever you want, right? These are parabolas, so you could easily just do calculus. You could just say, hey, take the derivative, and it's x squared something, and you get whatever, 2x this and that, and you say, all right, let's minimize that. You could do that. You don't have to use an optimization thing, but you just say, well, the one tool I know how to do is univariate optimization. How do I go from multivariate optimization down to univariate optimization? You just basically turn your multivariate function into univariate functions, a series of these things, and you just perform univariate optimization at each iteration. Okay, that is it for today. Last view quiz answer is the letter A as in apple. We'll call it a day here, and have a great rest of your Monday. We'll see you on Wednesday, and yeah, welcome to week 8.